Welcome. Today we're diving into the fascinating world of organic chemistry. Whether you're a complete beginner or just brushing up on the basics, this journey will help you build a strong foundation. We'll explore what organic chemistry is, why it matters, and how it connects to everyday life. From the food we eat to the medicines we take, organic chemistry is everywhere. Let's start by understanding the core concepts that make this subject so important and approachable. Ready to unlock the secrets of molecules and reactions? Let's get started with the basics and set the stage for your learning adventure. Organic chemistry is the branch of science that studies carbon-containing compounds. It's all about understanding how carbon atoms bond with other elements to form the building blocks of life. From simple molecules like methane to complex structures like DNA, organic chemistry explains it all. This field is essential for biology, medicine, and even materials science. By learning organic chemistry, you'll gain insight into the molecular world that shapes our existence. Let's break down the classification of organic compounds and see how they're grouped based on their structure and properties. Organic compounds are classified based on their structure and functional groups. The main categories include alkanes, alkenes, alkanes, aromatic compounds, and those with specific functional groups like alcohols, ketones, and acids. Each class has unique properties and reactivity. Understanding these categories helps you predict how molecules will behave in different reactions. As we move forward, keep these classifications in mind. They're the foundation for everything else in organic chemistry. Next, we'll explore how atoms bond together to form these diverse compounds. Hybridization is a key concept in organic chemistry. It describes how atomic orbitals mix to form new hybrid orbitals that make bonding possible. For example, carbon can form sp3, sp2, or sp hybrid orbitals, allowing it to create single, double, or triple bonds. This flexibility is why carbon is so central to organic chemistry. Hybridization determines the shape and stability of molecules, influencing everything from boiling points to reactivity. Understanding hybridization helps you visualize molecules in 3 dimensions, making complex structures much easier to grasp. Let's talk about sigma and pi bonds, the 2 main types of covalent bonds in organic molecules. Sigma bonds are the first bonds formed between 2 atoms, created by the head-on overlap of orbitals. They're strong and allow free rotation. Pi bonds, on the other hand, result from the side-to-side overlap of orbitals, usually forming after a sigma bond in double or triple bonds. Pi bonds add rigidity and affect the molecule's reactivity. Recognizing sigma and pi bonds is crucial for understanding molecular structure and predicting chemical behavior. Representing organic molecules accurately is essential for understanding their structure and reactivity. Chemists use several methods: bond-line or skeletal structures, condensed formulas, and Lewis structures. Bond-line structures simplify complex molecules by focusing on bonds and omitting hydrogen atoms attached to carbons. Condensed formulas provide a compact way to show groups of atoms. Lewis structures, meanwhile, display all atoms and lone pairs, making electron arrangements clear. Mastering these representations will help you read and draw molecules with confidence. Bond-line structures, also known as skeletal structures, are the most common way chemists draw organic molecules. In these diagrams, lines represent chemical bonds, and the ends or intersections of lines represent carbon atoms. Hydrogen atoms attached to carbons are usually omitted for simplicity. This method makes it easy to visualize large and complex molecules without clutter. By practicing bond-line structures, you'll quickly become comfortable interpreting and drawing organic compounds, which is a vital skill for any chemistry student. Condensed structural formulas offer a more compact way to represent organic molecules. Instead of drawing every bond, atoms are grouped together, and their connectivity is shown in a linear fashion. For example, propane can be written as CH3CH to CH3. This method is especially useful for quickly writing out molecules in reactions or when space is limited. While it may seem less visual than bond-line structures, condensed formulas are efficient and widely used in textbooks and exams. Lewis structures are a detailed way to show all atoms, bonds, and lone pairs in a molecule. Each atom is represented by its symbol, with lines for bonds and dots for lone electrons. This method is invaluable for understanding electron distribution, predicting molecular shape, and identifying reactive sites. Lewis structures are especially important when discussing reaction mechanisms, as they make electron movement clear. Practice drawing Lewis structures to strengthen your grasp of molecular details. Isomerism is a fascinating concept in organic chemistry. It refers to compounds that have the same molecular formula but different structures or arrangements of atoms. Isomers can have very different physical and chemical properties, even though their formulas are identical. Understanding isomerism is crucial for recognizing the diversity of organic molecules and predicting their behavior. Let's explore the main types of isomerism: structural, geometrical, and optical, each with unique characteristics. Structural isomers are compounds with the same molecular formula but different connectivity of their atoms. This means the atoms are linked in different ways, leading to variations in structure and properties. For example, butane and isobutane both have the formula C4H10, but their atoms are arranged differently. Structural isomerism is the most basic form and sets the stage for more complex types. Recognizing structural isomers helps you understand how small changes can lead to big differences in chemistry. Geometrical isomerism, also called cis-trans isomerism, occurs in compounds with restricted rotation, usually due to double bonds or ring structures. In these isomers, atoms or groups are positioned differently in space, leading to distinct physical and chemical properties. For example, cis-2-butene and trans-2-butene have the same formula but differ in the arrangement of their substituents around the double bond. Geometrical isomerism is important in understanding the behavior of alkenes and cyclic compounds. Optical isomerism arises when molecules have chiral centers, carbon atoms bonded to four different groups. These isomers, called enantiomers, are mirror images of each other but cannot be superimposed. Optical isomers often have identical physical properties but differ in how they interact with polarized light in biological systems. This concept is vital in pharmaceuticals, as one enantiomer may be therapeutic while the other is inactive or harmful. Understanding optical isomerism helps explain the complexity of molecular interactions. Visualizing isomers in three dimensions is key to understanding their differences. 3D models help you see how atoms are arranged in space, making it easier to distinguish between structural, geometrical, and optical isomers. Tools like molecular model kits or computer animations can bring these concepts to life. By practicing with 3D representations, you'll develop a deeper intuition for molecular shapes and how they influence chemical behavior. Naming organic compounds may seem daunting, but the IUPAC system makes it systematic and logical. The International Union of Pure and Applied Chemistry, IUPAC, provides rules for naming molecules based on their structure. By following these rules, chemists can communicate complex information clearly and unambiguously. Let's break down the steps for naming organic compounds, starting with identifying the longest carbon chain and functional groups. First step in naming an organic compound is to identify the longest continuous chain of carbon atoms. This chain determines the base name of the molecule, such as methane, ethane, propane, and so on. If there are multiple chains of the same length, choose the one with the most substituents. This step sets the foundation for the rest of the naming process, ensuring consistency and clarity in chemical communication. Once you've found the longest chain, the next step is to number the carbon atoms. Start from the end nearest to a substituent or functional group. This ensures that the substituents get the lowest possible numbers, which is a key rule in IUPAC nomenclature. Proper numbering helps avoid confusion and makes it easy to identify the structure of a compound just from its name. Substituents are groups attached to the main carbon chain. Common examples include methyl, ethyl, and halogens like chlorine or bromine. Each substituent is named and its position on the chain is indicated by a number. If there are multiple identical substituents, prefixes like di, tri, or tetra are used. This step adds detail to the compound's name, making it precise and informative. Finally, combine the base name, substituents, and their positions to create the full IUPAC name. The name should be clear, systematic, and unique to that compound. For example, 2-methylpropane tells you exactly where the methyl group is attached. Mastering this process allows you to name and interpret a wide variety of organic molecules with confidence. Let's put the nomenclature steps into practice with a few examples. We'll walk through the process of naming simple alkanes, alkenes, and compounds with functional groups. By applying the rules step by step, you'll see how systematic and logical the IUPAC system is. Practicing with real examples will build your confidence and help you tackle more complex molecules in the future. Electronic effects are crucial for understanding how and why organic reactions occur. They describe how electrons are distributed in a molecule and how this affects reactivity. The main types include inductive effects, resonance, hyperconjugation, and the electromeric effect. Each effect influences the stability and behavior of molecules in different ways. Let's start by exploring the inductive effect and how it operates in organic compounds. Inductive effect refers to the shifting of electrons along a chain of atoms due to differences in electronegativity. Atoms like fluorine or chlorine pull electron density toward themselves, creating partial charges. This effect can stabilize or destabilize certain parts of a molecule, influencing its reactivity. Understanding the inductive effect helps explain why some molecules are more acidic or basic than others, and why certain reactions occur more readily. Resonance describes the delocalization of electrons across multiple atoms, creating structures that can't be represented by a single Lewis structure. Resonance stabilizes molecules by spreading out electron density. For example, the carboxylate ion has two equivalent resonance forms, making it more stable than if the electrons were localized. Recognizing resonance is essential for predicting stability and reactivity in organic compounds. Hyperconjugation is the interaction between sigma bonds and adjacent empty or partially filled orbitals. This effect helps stabilize carbocations and alkenes by allowing electrons to spread out more. Hyperconjugation explains why some molecules are more stable than others, even if they have the same number of atoms. It's a subtle but important concept that adds depth to your understanding of organic chemistry. Electromeric effect occurs when a molecule temporarily shifts electrons in response to an attacking reagent. This effect is usually seen in compounds with double bonds, where electrons move to facilitate a reaction. The electromeric effect is short-lived but plays a key role in many organic reactions, especially those involving addition to alkenes or carbonyl groups. Animations and diagrams make electronic effects much easier to understand. By seeing how electrons move during reactions, you can grasp why certain products form and why some reactions are faster than others. Visual tools help clarify abstract concepts, making them more accessible and memorable. Let's use these visual aids to reinforce what we've learned about inductive, resonance, hyperconjugation, and electromeric effects. The action mechanisms explain how and why chemical reactions occur at the molecular level. They show the step-by-step movement of electrons, often using curved arrows to indicate electron flow. Understanding mechanisms helps you predict the products of reactions and design new ones. Let's start by exploring how to read and draw reaction mechanisms, focusing on the role of electrons. Curved arrows are the language of reaction mechanisms. They show the movement of electron pairs during each step of a reaction. A full arrow indicates the movement of two electrons, while a half arrow shows the movement of one. By mastering curved arrow notation, you'll be able to follow and predict the course of organic reactions with confidence. Most organic reactions occur in a series of steps, not all at once. Each step involves the breaking and forming of bonds with electrons moving from one atom to another. By analyzing each step, you can understand the overall transformation and identify key intermediates. Stepwise mechanisms make complex reactions manageable and logical. Nucleophiles are species that donate electrons while electrophiles accept them. These roles are central to organic reactions. Nucleophiles are often negatively charged or have lone pairs, while electrophiles are positively charged or electron efficient. Understanding these concepts helps you predict which molecules will react together and what products will form. Organic reactions can be grouped into several common types: substitution, addition, elimination, and rearrangement. Each type has characteristic mechanisms and outcomes. For example, substitution reactions involve replacing one group with another, while addition reactions add atoms to double or triple bonds. Recognizing reaction types helps you organize your knowledge and approach new problems systematically. Substitution reactions: one atom or group in a molecule is replaced by another. These reactions are common in organic chemistry and can proceed via different mechanisms such as SN1 or SN2. Understanding the conditions and outcomes of substitution reactions helps you predict products and design synthetic routes. Addition reactions involve adding atoms or groups to double or triple bonds, converting them into single bonds. These reactions are especially important for alkenes and alkenes. Addition reactions can be initiated by acids, bases, or even light. Understanding addition mechanisms helps you predict how unsaturated compounds will react and what products will form. Elimination reactions remove atoms or groups from a molecule, often forming double or triple bonds. These reactions are the reverse of addition and are crucial for creating unsaturated compounds. Common elimination mechanisms include E1 and E2. By understanding elimination, you can manipulate molecular structures and create new functional groups. Rearrangement reactions involve the shifting of atoms or groups within a molecule, creating new structures. These reactions can lead to unexpected products and are important in both synthetic and biological chemistry. Understanding rearrangement mechanisms helps you anticipate possible outcomes and design efficient syntheses. Carbocations are positively charged carbon intermediates that play a key role in many organic reactions. They are formed during mechanisms like SN1 and E1. Carbocations are stabilized by electronic effects like resonance and hyperconjugation. Recognizing carbocation intermediates helps you understand reaction pathways and predict products. Carbanions are negatively charged carbon intermediates, often formed in reactions involving bases. They are highly reactive and can act as nucleophiles. Carbanions are stabilized by electron-withdrawing groups and resonance. Understanding carbanion intermediates is essential for mastering organic reaction mechanisms. Free radicals are intermediates with unpaired electrons. They are formed in reactions involving light or heat, such as halogenation of alkanes. Free radicals are highly reactive and can initiate chain reactions. Recognizing free radical mechanisms helps you understand a wide range of organic transformations. Transition states are high-energy, unstable arrangements of atoms that occur during a reaction. They represent the point of maximum energy along the reaction pathway. Understanding transition states helps explain reaction rates and why some reactions are faster than others. Visualizing transition states is key to mastering reaction mechanisms. Energy diagrams graphically represent the energy changes during a reaction. They show the energy of reactants, products, intermediates, and transition states. By analyzing energy diagrams, you can predict reaction feasibility and compare different pathways. These diagrams are powerful tools for visualizing and understanding organic reactions. Let's practice drawing reaction mechanisms using curved arrows. We'll start with simple substitution and addition reactions, breaking them down step by step. By following the movement of electrons, you'll see how reactants are transformed into products. Practicing these skills will make you more confident in tackling complex mechanisms. It's easy to make mistakes when learning reaction mechanisms. Common pitfalls include incorrect use of curved arrows, forgetting to show all intermediates, or misidentifying nucleophiles and electrophiles. By being aware of these challenges, you can avoid errors and develop a more accurate understanding of organic reactions. Mastering reaction mechanisms takes practice and attention to detail. Focus on understanding electron movement, practice drawing mechanisms regularly, and review common reaction types. Use visual aids and animations to reinforce your learning. With persistence, you'll become skilled at predicting and explaining organic reactions. Now that you've explored the basics of organic chemistry, it's time to connect the dots. Each concept, from hybridization to reaction mechanisms, builds on the others. By seeing how these ideas interrelate, you'll develop a holistic understanding of organic chemistry. This integrated approach will serve you well as you tackle more advanced topics. Congratulations! You've covered the foundational topics of organic chemistry, from basic concepts and structural representations to isomerism, nomenclature, electronic effects, and reaction mechanisms. These building blocks will support your future studies and help you succeed in more advanced chemistry courses. Keep practicing, stay curious, and remember that every complex molecule starts with these simple principles. Your journey in organic chemistry has just begun.